atoms, molecules, and ions. We're first going to look at Dalton's atomic theory, and he was aware of two natural laws. Law of conservation of mass, law of constant composition. Lavoisier was the one who determined the law of conservation of mass. He carried out an experiment in which he decomposed mercury to oxide. And what he found was he started with 2.9 grams, and he ended up with a total of 2.9 grams. So the mass before equals the mass after a chemical reaction. And so the law of conservation of mass says that the total mass before equals total mass after, determined by Lavoisier. And then in 1799, Joseph Proust found that copper carbonate has a fixed composition. Now this particular chart, table, shows the reaction of magnesium with oxygen to form magnesium oxide. There are three different trials, starting with different masses of magnesium, but what's important here are the ratios of magnesium to magnesium oxide here at the very end. Those ratios. Magnesium oxide is always 60% magnesium and 40% oxygen by mass, regardless of how much I start with. And so Proust determined the law of constant composition, which says a chemical compound always has the same proportions by mass of its constituent elements. Dalton's atomic theory, 1808. Not all parts of his atomic theory are correct as we know them today, but it was very important at his time. Number one, each chemical element is composed of minute, indivisible, indestructible particles called atoms. Now we know today that atoms can be divisible, but again, at his time the technology was not there to dispute his atomic theory. Number two, all atoms of an element are alike in mass and other properties, but the atoms of one element are different than those of other elements. Today we know there are certain things as isotopes, so all atoms of an element are not alike because there are certain things called isotopes. We'll get to that later. And then number three, in chemical compounds, atoms of different elements combined in simple numerical ratios. They have to be whole number ratios, and this is true. You have to have like H2O, 2 atoms of hydrogen, 1 atom of oxygen. Have to be whole number ratios. Dalton's atomic theory can explain the law of conservation of mass and the law of constant composition. Now this is a little theoretical here, but it can explain the law of conservation of mass first. If I take 12 grams of carbon and 32 grams of oxygen, law of conservation of mass says that I'm going to end up with 44 grams of carbon dioxide. Now, because the mass before has to equal the mass after. Now 12 grams of carbon, if you look on the periodic table, is actually 1 atom of carbon. And 32 grams of oxygen is actually 2 atoms of oxygen. And when you put 1 atom of carbon and 2 atoms of oxygen together, you get 1 atom of carbon dioxide, CO2. And the mass of 1 carbon and 2 oxygen atoms is the same before and after the reaction. Dalton's atomic theory can also explain the law of constant composition. Carbon monoxide, for example, is always 43% carbon and 57% oxygen by mass. So a sample of carbon monoxide contains large numbers of molecules, and each molecule contains 1 atom of carbon and 1 atom of oxygen. Now let's kind of break this down. An oxygen atom weighs 1 1/3 times more than a carbon atom. Go back to the periodic table. Oxygen has a mass of 16. Carbon has a mass of 12. So that's where we get 1 1/3 times that of a carbon atom. So here's oxygen, 4/3 C. I'm putting everything in simplest terms. Carbon is 3/3 carbon. My sum will be 7/3 carbon. Well, 4/3 divided by 7/3 would give you 4/7, and this is for oxygen. And 4/7 is always 57%. And then carbon would be the 3/7 of the total mass, which would be 43%. So this is just kind of putting everything into like terms. That's why I used carbon here instead of oxygen. Okay, now we're going to look at subatomic particles. First of all, the electron. In the latter part of the 1800s, a few scientists carried out a series of experiments in which they had a sealed metal plates into the ends of a glass tube that was evacuated of air, and they applied a voltage of several thousand volts across the metal plates. We had the cathode, we have the anode, and here's kind of what a cathode ray tube looks like. And in a cathode ray tube, the particles always streamed toward the anode, so the particles always streamed this way toward the anode. So these were called cathode rays. They traveled from cathode to anode. And electromagnetic theory tells us that when a moving charged particle behaves like a magnet, it can interact with electric and magnetic fields. Since the cathode rays were attracted by the positively charged plate, they must consist of negatively charged particles. J.J. Thomson is actually the guy who's credited often with discovering cathode rays, which are these streams of negatively charged particles emitted from the cathode ray tube. And Thomson determined the ratio of electric charge to mass for cathode rays. So the cathode ray tube, J.J. Thomson, we were able to get the charge to mass ratio for an electron. Now the name for an electron was actually given by George Stoney, but J.J. Thomson is the guy who's credited with the discovery of electrons. In 1909, Robert Millikan performed in the oil drop experiment, and he determined the charge of an electron. Now, don't worry about these actual numbers for charge and charge to mass, but when we put the two experiments together, here's Millikan's experiment, the charge. Here's Thomson's experiment, the charge to mass. We were able to get the actual mass of an electron, 9.1 times 10 to the negative 28 grams, which is very small. It's about 2,000 times smaller than that of the hydrogen atom. In 1886, Eugene Goldstein did some experiments with a glass tube with a perforated cathode, and it contained a gas at low pressure. And in his tube, there was a stream of positively charged particles whenever a voltage was applied. A canal ray tube looks very similar to a cathode ray tube. The difference is the particles stream toward the cathode. They stream toward the negative electrode. We know they're positively charged because they travel toward the cathode, and the positively charged particles, which were later became known as protons, are formed when cathode rays knock electrons off gas particles. And so Eugene Goldstein is credited with the discovery of protons around 1886 from the canal ray tube. J.J. Thomson proposed a model for his atom. We had Dalton's model for the atom, was just an empty sphere. Then we had J.J. Thomson. Thomson's model became known as the plum pudding model. The electrons are kind of stuck in place like a chocolate chip cookie, but he called it plum pudding. And the positive charge is spread throughout. So J.J. Thomson, immediately after Dalton, came up with his model around 1900. And this was a model that was accepted for some time, the plum pudding model, where the electrons are stuck in place and the positive charge is spread throughout the atom.